For another lesson with Mr. M. Today we are going to be talking about circular motion. And so as you can see on the right here, we have someone in the hammer toss. And basically in the hammer toss is they twirl this weight around and then they throw it. And so today we're going to be talking about some of the physics behind objects that are being twirled around or objects that are undergoing circular motion. Okay, so let's get to it. Alright, first, our objective for today is we want to be able to explain the forces present of an object undergoing uniform circular motion, and we want to be able to calculate its centripetal acceleration and its centripetal force. So we're going to be taking a look at two equations today. Some of the key terms that we're going to be going over have to do with uniform circular motion, centripetal acceleration, and centripetal force. So as you can see, this word centripetal here is a key word in itself. Okay? So in terms of our uniform circular motion, whenever you hear the word uniform, you ought to kind of be thinking of something along the lines that everything is doing the same thing, or there's something constant about it. And that's what we see here in uniform circular motion. It's defined as the movement of an object at a constant speed around a circle with a fixed axis. So some examples, as I already mentioned, the athletes who perform a hammer throw, or if you've ever been on the swing ride at the carnival, okay, you in the swing, as it twirls you around and around, you are undergoing uniform circular motion. Okay, these are just objects that are going around in a circle at a constant speed. The key point with uniform circular motion is that the velocity of these objects, or the speed of these objects, is tangent to the circle. So you should kind of think back to your math class here. A tangent line is that line, it goes and intersects a circle at one point. Okay, it's a straight line that intersects a circle at one point. Okay, so in our circular objects, and so here this visual is showing that the object is going counterclockwise or in this direction. That velocity at this point in its path is tangent to the circle. And on this point, we can see it when it gets to this point in its path is tangent at this point. Okay? And what this means is if we were to let go of this object at this point, that object is actually going to continue along that straight line path. Okay? So if we're twirling this object around and around and we let go of it right here, that means that the object will continue to go in a straight line in that path. Okay? So in terms of athletes that are doing the hammer throw, they kind of have to be careful of when they actually release their hammer so that it goes into fair play. Okay? Now, in terms of our centripetal acceleration, quick review here. There are three ways to accelerate. We can either speed up or we can slow down, and these two fall under the category of a change in speed or a change in velocity, which is one of the ways that we define acceleration. But there's also a third way that is going to apply to these objects undergoing circular motion, and that's when we change our direction. If we change our direction, then we are accelerating. So in uniform circular motion, we are constantly changing direction because it's constantly moving. Okay? So what keeps the moving object from going off on that tangent? Okay, as we just talked about. Well, the string or the rope or whatever is attaching itself to the object is pulling that object towards the center at every point. And when this happens, it creates an unbalanced force towards the center. Now, if you think back to Newton's second law, an unbalanced force causes acceleration. So the unbalanced force in this case is that force that's pulling the object towards the center. And that's where we get our centripetal acceleration. Whenever we use the word centripetal, it means something that is center seeking, or something that's going towards the center. As one of our objectives stated, we wanted to be able to solve for the centripetal acceleration of these circular objects. And so here is our equation, okay? And we have our acceleration here designated with a subscript of the c, okay? And that c stands for the centripetal acceleration. And this equation is a little bit different than your normal acceleration equation. Here we see we have v squared over r, okay? And the v here is our velocity or our speed, and the r is our radius. So we're going to be given some distance, and that's obviously the radius of the circle. Now in terms of our centripetal force, okay, that's that force, that unbalanced force that we mentioned with our centripetal acceleration, okay? And the unbalanced force towards the center of the circle always causes objects to travel in the circular motion. And we also have an equation for this as well. Very simple. It looks quite like Newton's second law of F equals ma. Okay, but in this case, when we're using it to solve for centripetal force, you see that we have to use the centripetal acceleration. Okay, and I'm going to show you in another video how we can use both of those equations. But for right now, I want to actually show you what this centripetal force looks like, okay? In terms of like the force diagrams and so forth. Let's make sure I've got my circle, okay? So here we have our object undergoing circular motion. We're going to say that, just kind of like with the hammer toss, here's going to be the center of our circle, and then we're going to have it attached to an object, very similar to the hammer toss. Okay. In this case, let's say that we're moving in a clockwise position. Okay, so we're going clockwise in our rotation as we're twirling this around. And a quick review: the velocity of this object as it's going around and around, that velocity is in a tangent force, a tangent vector to the circle. All right, so let's designate that this is our velocity here. That's our v. Okay. And one of our questions was, well, what's actually keeping this object from not going in that straight path? Why does it continue to go in a circle instead of on this tangent line? Well, as I mentioned, there is a force from the tension of the string or whatever that's holding it, and that string is pulling on it, and it's pulling on it towards the center. That right there is our centripetal force. Okay, that's our force. All right. And if we were to do this at every single point in the path, so let's say at this point in the path, okay, well, once again, our velocity is going to be tangent to the line, meaning if we let it go right there, that object would continue along this straight path. But once again, that string is tugging on it, it's pulling on it towards the center. And if we were to do this at every single point, we would start to see that at every single point, that string is pulling that object towards the center. Okay? And that's what keeps these objects in the circular motion. Okay? And keep in mind that the centripetal force will always keep that object going into a circular motion. Okay? All right. So hopefully this lesson was helpful to you. Pardon this. Hopefully this lesson was helpful to you in determining what centripetal acceleration is, what centripetal force is, and gives us the basics for uniform circular motion. Thanks for watching.